Okay, thank you very much for introducing me. To give you this presentation about challenges and possibilities with robots using in 3D additive manufacturing, 3D printing processes. A kind of a little bit of off topic for normal printing applications, but as we heard before, it's a important new market niche and technology for a combination in functional printing and automation with robotics, and I think it might give you some kind of outlook for possible future applications. About KUKA, we're one of the leading companies for robotics and automation. I'm, as told you before, with KUKA since 2004 and acting now as a business development manager with KUKA, responsible for additive manufacturing, additive printing processes at KUKA, mainly with the background using our main products, our robots in additive manufacturing processes. My presentation should give you an overview about challenges, possibilities, a couple of application examples we've done in the past with our systems in robotic 3D printing processes. There are mainly three applications where robots are used in additive manufacturing process, and three main materials we see markets to use robots for additive manufacturing and 3D printing. So the main materials which are used for robot-based additive manufacturing are plastic materials, metal materials, and concrete materials. These three different types of materials use the flexibility of a robotic system from very small to very large scale robot workspaces, which the robots can be used in, from very small and handy kinds of robots which are more or less used for plastic production, as well for metal printed solutions. If you're going into concrete printing solutions, you need one of the main advantages of robotics in terms of reach, to give you a high flexible system which can work on a large scale printing opportunity. Where are these parts made out of these materials used? Prototype printing, spare part printing, small series production, design aid production, and new technologies, new market for metal printing parts in combination with functional printing, as well as on the concrete side where walls are produced by robot-based printing solutions, and other parts more going into furniture and design environmental things. Here you see a lot of application examples, what has been done in the near past, combined with robot-based solutions. So you see there are a lot of applications, new developing, using robotic systems in 3D printing applications, starting from plastic printing, going forward into metal printing technologies for aerospace applications and new automotive applications, and ending up with concrete printing on columns and other articles. Okay, what are the main advantages using a robot? So a robot is very flexible. So from tiny ones going up to very large robots, we have payloads starting at 3 kilograms for very tiny and thin and accurate 3D printing processes, going up to real heavy robotic systems, going up to a payload of more than 500 kilograms with a reach of almost in radius, giving you the opportunity to print almost sizes of 3 by 3 meters in width, with a necessary height, and things like that, which is a kind of real flexibility for large-scale printing. And this in combination with a 6-axis robot in all terms of freedom and flexibility in your process. This is the main advantage of using a robot in a 3D printing process, that you get a real flexible system which gives you the opportunity for new ways to do the additive manufacturing and 3D printing process with highly flexible and freedom of orientation. So with a 6-axis robot, you don't have to stay within one orientation. You can really print on either existing parts, and this is the next step going to functional printing, to have existing parts where you do an additive process on existing parts, and this might be a real good possibility to add 3D printing with functional printing for future applications. And what's very helpful, it's quite easy to scale from very small to large scale printing, from small geometrical parts going up to a larger scale printing on large parts, where the use of the same technology, the same control environment, the same basic setup of your system, only with the flexibility coming from a small robot system going up to a very large system. So availability and cost is as well one key aspect. So a robot is a standard system, so it's a highly cost-efficient solution to having a 6-axis system. There are as well additional axes available on the market, so it's quite easy to place a robot, for example, on a linear track, and so you extend the work range of a robot and multiply the work range, only adding one additional axis, and that helps to build up very cost-efficient, flexible solution doing whatever kind of process. And in combination with the additive manufacturing and 3D printing process, a robot system as well brings the benefit to be highly flexible. So you get the opportunity and the chance to add processes as well, not only to do the additive or 3D printing process. It's as well possible using some kind of tool changes to switch from one process to another process and add these processes in combination in a production system. And this is for sure one other argument for going with a robot-based system in these kinds of processes. So I already mentioned some topics about printing on previously impossible structures or without support structures. By the use of this 6 degrees of freedom from a robot system, it's possible now to do other jobs formerly not possible. Printing on existing surfaces with functional implementation. Repair printing is a very important topic for metal printing applications, to use robots in repair printing for very expensive toolings and things like that. Hybrid printing, additive manufacturing in combination and together with the other processes. Here we come to the process chain using a robot in additive manufacturing processes. What you see, the part for the offline preparation using a robot in printing, additive manufacturing processes, and the real process on a control and robot side is, this just should give you an indication. It's very important to have a proper working offline process chain, which means you start somewhere with the CAD drawing of your final part, and then you have to have the right kind of additional 3D printing software, doing a slicing of your CAD files in the right kind of application equipment you're going to use. So it's not using a standard slicing software doing the doing the creation of your path for the additive manufacturing process, it's important to use the right kind of software with the right kind of functionality and process integration already at this time for a later on robot-based 3D printing process, which brings the right quality and features within to really use this 6 degrees of freedom of a robot in the right way. And by the use of this system, you generate an optimized tool path for the robot, which later on will do the 3D printing process based on the robot movements and so on. And finally, which is as well very important, to have some kind of offline simulation, which helps you to eliminate any kind of problems during the process, to highlight any kind of singularities coming from a robot kinematics, and the final part will be the code generation with a fitting post-processor in a CAD/CAM software to generate a best kind of code for a robot-based system. This is as well important that the code is accordingly to the best performing settings for robot systems, that you have the right settings for a best synchronization between path movements and process functionality in the additive material process. That's very important, and that's all in the offline world, and only at that time you go on the real control system. And here it's as well very, very important to have the synchronized functionality between process control and path motion control, as it's only a successful process if you really have a real synchronization between path motion velocity, process, flow rate, things like that, to have an optimized process success and a real good solution. And that's very important. And in every part of this process chain, it's very important to use the right kind of tools, the right kind of systems, which bring in the right kind of functionality and features to use all the benefits of a robot-based solution and system in these processes. And that's very important. There are special tools you should use in here. Not only go for standard slicing softwares and things like that, what I would recommend to eliminate any kind of challenges maybe in the offline world as well on a robot control system in combination with the process. One example, it's not done, but it's from SoftDream, a project. They sum up all the challenges using robots in printing processes. So there are a lot of things going on from offline path planning, going into the printing path, going into pre-processing, planar, non-planar, infill patterns, print on part, which might be very important in a printing and a functional printing environment, semi-finishing products, fast printing, and very accurate large-scale printing. So what I want to show you is it's not a linear, one step after another, complexity. It's a multi-function or multi-directional complex topic if you're going into a additive manufacturing process using a robot system. And it's very important to have the right kind of partners within this technology to come to a successful solution and use the right kind of tools and things like that to really come up with a successful solution. So here you see the right kind of slicing. Only by using a kind of slicing functionality and doing that in the right way, it's possible to generate a application like you see here with a non-planar outcome of the product. And this technology and functionality is very important. in the offline world, but it's as well very important to use this in a synchronized way as well on a real machine, on a real robot system in a synchronized way. Otherwise, you never will end up with the product you plan to produce with your robot system and your process control if you don't think about all these topics in an early stage and in a setup of your complete solution. And that's just an important thing. A real good setup of your complete system process control. So as soon as your robot and your motion controls are not the way they should be, you generate outcoming like this, what you really don't want to have. You want to have a smooth, gentle and constant pass velocity. Your material flow rate should be according to your real programmed flow rate, that you get maybe a little bit more amount of volume at that part you really want to have it, and not in areas you don't want to have it. And that's very important to consider and think about in an early stage. Otherwise, your solution will not be as successful as you want to have it. Okay, some new markets, and I mentioned the applications before. In the following slides, I will show you real application examples. Here, a couple of pictures for plastic, concrete printing or metal printing, and you already see advantages of a robot system. So the large workspace of a robot system is one of the main advantages. So this gives the flexibility and the possibility to do an additive printing process in new ways and new possible flexible solutions for the future. Exactly. Here one example for plastic where new possibilities comes up to generate from furnitures going to carbon reinforced materials, 3 printed parts, from one example going for a complete boat, or a new possibility in piping in automotive and car manufacturing industry to produce in an early stage prototypes in a flexible way with much lower costs than existing systems to generate prototype parts. This is the application video where parts for this ship I showed you before are produced in a robot-based solution, and here you can see it's very important to have this synchronization between robot movements and flow rates and things like that to generate the most accurate results. And furthermore, the complete robot system has to be set up in a very accurate way, and the combination between offline and a real online control system is very important for a successful end product. So maybe, as you can see, the complete ship was not, or boat was not printed in one printing process. So it was produced in segments, and it was produced by a customer of ours, by an integrator of ours. Developed this process technology on their own, and this is their key technology know-how to use robot systems in that way, in a additive manufacturing process to produce these. This is the example shown from BMW, where prototype parts are printed with a robotic solution as well. You can see mainly as well in a set direction. So the heights here, in combination with the width of this part, give you that kind of flexibility to produce new parts in a very cost-efficient way. Even if this is not a real video, but this video simulation should show you the possibilities how to use the robot-based system in real applications, and this is a real applications which was implemented at BMW. Here we see other examples. So this is one example for creating new facade elements out of plastic, which will be later on be coated with carbon concrete material for facades on housings. But the base structure is printed in a 3D printed process, and that might be as well give some possibilities for future, for architecture to use as well the 3D printing process in combination with functional printing processes to add lightnings or already currents and power possibilities in the structure of the part. So this is another example for the aerospace industry to generate highly flexible parts with plastic printing, in addition with carbon fiber tabling to improve the material behaviors, and this can be done with one system, like I mentioned, in a flexible way. You see this process head is a very large process head, so it's a combination not only for a real 3D printing additive manufacturing process, is as well a combination for tabling and doing this in a combined process, and using that kind of technology head might be some possibilities for the future as well, to bring as well in functional functions into at this time more low batch parts for sure, but to start with functional printing. This is one example coming from the US, done by Relativity, a aerospace company producing vessels and parts for rockets, and they use our robots and use robots at all to generate these rocket vessels in a very flexible way, in a very cost-efficient way, like you've seen here on this video, with as well adding a additional access for the set workspace to use the robot system in a very flexible way to have the possibility to generate whatever kind of vessel sizes and dimensions and adding in the right way. And here finally one example for concrete printing. What you can see, this is a concrete spraying application. There's as well a concrete extrusion process on the market. This is an example of concrete spraying as well to showcase the flexibility of a system here in combination with a rotating table. Like I mentioned before, a robot system, it's pretty easy to combine with additional access and additional possibilities. Here we are. Okay, outlook. Yeah, I mentioned a couple of times, functional printing should be possible. So I know in research environments at the Fraunhofer in Germany or in other places and institutes, there are a lot of things going on in functional printing, which will combine 3D printing with the possibility to integrate functions in the generated part. Textile industry is a very important market for printing, and the use of a robot system like you see here will help to be more flexible for the future. And I think this is one of the outlooks to use additive manufacturing processes based on robotic systems for the future. And I'm really looking forward to to have conversations with you where you see potential use of robotic systems in printing processes afterwards. And that's from my side, and I would be happy to answer any kind of questions from your side at this time. Okay, thank you very much.